Hello. Mhm. Is there any topic or question you guys want to go over for 8B quiz tomorrow?
Yeah. Can you explain about tautomerization?
Tautomerization, yeah, let's do that. Okay. Hey Madison. So yeah, today we're gonna talk about enolate tautomerization, which was the one thing that we didn't go over earlier. So this is going to be tautomerization process right here. Tautomerization. Right. So to do that, we have to know what an enol and enolate is. Oh, hey Kelly, how did your 118A quiz go today on spectroscopy? Right. Sad. Is there an easy way to recognize the pKa for enolates? So the pKa for enolates is going to be different depending on the surrounding groups around it. And that's going to be what I would recommend putting on the note card. But I would also understand like what makes the difference between them. Like what makes the difference between like what makes a higher pKa versus a lower pKa. So I can go over that too today. Okay. So but first let's go over tautomerization. Now tautomerization is going to occur when we have this structure, which is called an enol, right? And an enol is going to be when we have an alkene next to an alcohol. Enol, right? This is going to spontaneously convert into a carbonyl, carbon double bond oxygen. And in most cases, the carbonyl form.
No, Benny just called me fat in the kitchen.
When did I do that? No,
you,
she actually
you
called me
can't do
fat.
that.
She called me fat,
He
actually.
called me.
I don't
fat.
remember precisely what she said, but I remember thinking to myself, wow, she called me fat. And I was gonna say, you can't
Hello,
do
hello.
that to me.
Okay, so this is an enol here when we have an alkene next to an alcohol. So for 118B students, this is midterm 2 review with the enol tautomerization. When we have that enol, it will spontaneously naturally convert into the carbonyl like that, right? There's gonna be some exceptions when the enol form is favored, and that's when we have resonance stabilized enols, right? So let's say we have that enol right there, but we tautomerized it into the carbonyl. Before, this molecule is aromatic, stable, right? But when we tautomerize, like let's say this enol here into this carbonyl right here, that's gonna be unstable, like that. So that's when we know that this enol here is gonna be major over the carbonyl. Another example would be something like this. Where that enol form is going to be major over this carbonyl form right here, right? The reason why is because we see that in this enol form, it's okay, that this is more conjugated because there's more resonance going on in the system, conjugated system. But we see that in this carbonyl form right here, there's an sp3 roadblock right there blocking resonance. So this system here is no longer fully conjugated. It can no longer do resonance like that. Okay, so let me show you guys the mechanism really quick. In acidic conditions, converting an enol to a carbonyl. So let's say I have this enol right here. Which atom gets protonated if, let's say, I have H2SO4 strong acid floating around? Which atom of the enol would get protonated? Yeah, we could go over Aldol condensation later today too. So
negative
huh?
charge on the double bond.
The double bond here gets protonated, specifically the alpha carbon of the double bond, right? It's not gonna be the OH here, right? That's a common mistake. Like some people said it's gonna be the oxygen of the OH. If the alkene was not there, then the OH would get protonated, right? But because this is an enol, this alpha carbon would get protonated. The reason why is because if I draw out the resonance structure for you, like this, I am going to get this structure where there's a full negative charge on this alpha carbon, making it more reactive than this oxygen right here. So to do that, we're gonna form a carbonyl, carbon double bond oxygen between this oxygen and carbon, but that's gonna break the octet rule for this carbon right here because it has 5 bonds now, 1, 2, 3, 4, 5. To conserve the octet rule, I'm gonna use this bond here to grab this hydrogen and kick out an HSO4 minus to give me this intermediate right here, and I'm gonna make this hydrogen that we grabbed invisible. We don't have to draw that hydrogen out. We can make it invisible. It's still there, but it's invisible. Now the last step here to get to the carbonyl is to neutralize the positive charge oxygen by deprotonating it with the conjugate base we just formed, which is gonna give us our carbonyl like that. Any questions on this mechanism? It's a very short mechanism, going from an enol to carbonyl.
What reagents do we see this happening with? Just anything that's like strongly acidic?
Yeah, anything that's strongly acidic, which could be H2SO4, H3O+, HCl, any of these non-nucleophilic acids like that represent a proton source, H+, is gonna do this mechanism. Right.
Thank you.
What's the name of this mechanism again?
The name of this mechanism is tautomerization.
Oh, okay.
Tautomerization. That's when we have an enol, and that's gonna spontaneously go into the carbonyl, right? But sometimes there's some cases where the enol is favored over the carbonyl, which is why I drew the arrow bigger going towards the enol. That's when the enol is stabilized by more resonance. That's when the enol is favored. So let's do that mechanism now, going from an enol to a carbonyl. Okay, so wait, we just did that. I mean, a carbonyl from an enol. Carbonyl to an enol. Carbonyl to an enol. So let's say we have this carbonyl right here, carbon double bond oxygen, and we want to get into this enol here. And we're still in acidic conditions here. What do you guys think is going to happen in the first step when we have a strong acid with this carbonyl here? What's going to get protonated?
The oxygen.
Yep, the oxygen of the carbonyl is going to get protonated. Grab that hydrogen, kick out the conjugate base, whatever it is. In this case, it's HSO4 minus. It could be Cl minus, it could be H2O, but in this case, since I'm using H2SO4, the conjugate base is HSO4 minus. So when we protonate the oxygen here, we get this intermediate where this oxygen gains a hydrogen and it loses one of its pairs of electrons because it used that pair of electrons to make that new bond between the oxygen and hydrogen. And it's now positively charged because it has 3 bonds, 1, 2, 3, and a pair of electrons. Okay, now once we have this, what is going to be the next step here? Our final step to reach this, what is that? This enol right here, right? This alkene next to an alcohol. There is like something that I have not drawn out yet. What would I have to draw out to complete this mechanism? If I want to draw out the complete mechanism for this last step, there's something that is invisible that I have not drawn out to complete this mechanism from this molecule.
Hydrogen? Your alpha?
Yes, alpha hydrogen, right. We're gonna deprotonate this alpha carbon by grabbing that alpha hydrogen. The bond between this alpha hydrogen and carbon right there is going to make a double bond right here and pop this double bond onto the oxygen to give me that enol right there. Now, that's the whole mechanism to go from a carbonyl to enol. You might ask, why did we not deprotonate the carbonyl oxygen and neutralize the carbonyl oxygen? Because that's gonna go reverse direction. It's gonna go backward, and that's an unproductive step. To make something new, a productive step, we are going to deprotonate the alpha carbon by drawing out the alpha hydrogen right there. Okay, so that's the mechanism for carbonyl to enol in acidic conditions. Now let's look at basic conditions really quick. Let's go from an enol to a carbonyl. Okay, can someone describe to me the steps of this mechanism? When I have this strong base and this enol right here, what is going to happen in the first step? Right.
Does the OH attack the alpha carbon?
So the OH here, because it can attack the alpha carbon, because this alpha carbon is electrophilic, there is another competing reaction. There is an acidic hydrogen here. What's faster, acid-base reaction or a nucleophile electrophile reaction?
Acid base, so it's gonna grab the hydrogen on the OH.
Yes, it's gonna grab the hydrogen from the OH. And I just realized what I just said. This alpha carbon here is also a nucleophile, because you know how when we draw out the resonance structure, that alpha carbon is gonna have a negative charge. This alpha carbon here is gonna repel that OH minus, because like charges repel each other. This is a nucleophile. This is like also a nucleophile base, but preferably a base. So the alpha carbon and OH minus would not interact with each other at all. They're gonna repel each other.
Okay.
Right. So we're going to deprotonate the alcohol here to give that oxygen a negative charge. And that gives me an enolate ion. This is an enol, alkene next to an alcohol. An enolate is a deprotonated enol when we have a negative charge oxygen right there. Okay. Now I'm going to bring in my proton source, water, that I just formed or that was present in the solution. What is going to happen between this proton source and this enolate ion here? What atom are we going to protonate in this enolate ion?
The oxygen?
So that looks like the case, right? If that alkene was not there, it would be the oxygen minus. But think about the resonance structure here. If I draw out the resonance structure, there's a negative charge on that alpha carbon. So if we want to get into the carbonyl here, if we protonate the O minus, that's going to go backwards to the enol. Right, because we just deprotonated the oxygen. If we like reprotonated the oxygen, that's going to go backwards. We're going to protonate this alpha carbon right here. Right, and we're going to do that by pushing one of the pairs of electrons on oxygen down to make a carbonyl bond, and have this alpha carbon grab a hydrogen from water, kick out the conjugate base to give us this final carbonyl product right here. Right. So when you see an enolate or enol right here, this alpha carbon is very sneaky because there is no negative charge there, but that alpha carbon is actually more nucleophilic and more basic than this O minus right here. Right. This O minus here is not going to be the base or nucleophile. It's going to be this alpha carbon for enols and enolates. For Aldol condensation, for Aldol dehydration, and Tautomerization. Okay. So that's the mechanism for enol to carbonyl. Now let's finish off this Tautomerization stuff with carbonyl to enol. So let's say I have this carbonyl right here, and I want to get into this enol right here, and I am in basic conditions, OH minus like that. What is going to get deprotonated here? What's the first step?
Does it go to does the OH attack the carbonyl carbon?
So that's a good yes, right? Because the OH minus can attack the carbonyl carbon if there is no what? If there is no
alpha hydrogen.
Yes. That alpha hydrogen is very sneaky, it's invisible. The OH minus here is gonna prefer to be a base instead. So it's gonna want to grab the alpha hydrogen instead of attacking the carbonyl carbon, right? If we had something like this structure right here, where the alpha carbons have 0 alpha hydrogens, then what you said would be correct, because there's no alpha hydrogen to worry about. There's no acid-base reaction to worry about. So this OH minus can only go to the carbonyl carbon and pop the double bonds with oxygen, right? But because there is an alpha hydrogen present, we're gonna grab that alpha hydrogen and generate our enolate ion like that.
So is it always the case with carbonyl to enol where we grab the alpha hydrogen to form that enolate ion?
In basic conditions, yes. And also in acidic conditions, yes, right? But in acidic conditions, before we grab the alpha hydrogen, we have to first protonate the carbonyl oxygen to make it positively charged. And then once it's protonated, then we grab the alpha hydrogen with the conjugate base we formed in the first step. Yep. If we go from a carbonyl to an enol, right? Because we want to create the enol, which means that we have to do an elimination step. Because when you have a double bond there, think of E1, E2 reactions, elimination reactions that creates double bonds. And this is our elimination step right here. This is an E2-like mechanism, right? The base grabs the hydrogen, creates a double bond, kicks out the leaving group. It doesn't really leave because it's a double bond. It kicks out one of the bonds onto the oxygen, but it's still attached by that one bond right there. Like that. So that's why it's E2-like, to create that double bond right there. Yep.
But it's like the same thing. Wait, yes. I don't really get it.
Like, it's the same thing for this mechanism and the acidic mechanism. But in the basic conditions, we directly attack the alpha hydrogen right away. We don't protonate the carbonyl oxygen because there's no acid for us to use to protonate it. And this strong base is strong enough to grab the alpha hydrogen right away. In acidic conditions, we have like H2SO4, H3O+. These are not bases. These cannot attack the alpha hydrogen right away, right? But what they can do is they can protonate the carbonyl oxygen first. And then when we do that, we kick out a conjugate base, which can be used to do the elimination step then now.
Okay, because of the because an acid reaction is more favorable in like the acidic conditions where we protonate it.
Yes, when we protonate it, because that becomes a better leaving group, and we actually have a base now. When we like deprotonate one of the acids here, we get like a base for us to use to do elimination, like E2 reaction to create that double bond. Yeah.
Okay, I see it.
Because if we have these strong acids here, there's no base for us to use to deprotonate the alpha hydrogen to grab the alpha hydrogen and do an E2 reaction. We first gotta like make a conjugate base for us to do the elimination reaction and create this double bond we want in the enol.
Okay, that makes sense.
Yeah, that's good.
What are some other examples of basic conditions, just to go over it real quick? Like
other examples of basic conditions would be anything that's negatively charged. So OH minus is a common one. OR minus is another common one. This R group here is a variable hydrocarbon. So it could be CH3, it could be CH2, CH3, CH2, CH2, CH3, isopropyl, like any random hydrocarbon chain. OR minus, alkoxide ion. It could even be LDA. It could be NaH with a hydrogen ion H minus. It could even be NaNH2, right? But when you see Na here, just think of that as a positive charge, and whatever is attached to it is negatively charged. So really, this NaH here is H minus. This NaNH2 here is NH2 minus. Because on the quiz, you could see KH as well, or KNH2, which is the same thing as H minus and H2 minus. So those are other bases that you might see.
Thank you.
Yeah. Now, once we have this right here, then we're going to use our proton source, water. And now, you know how previously I said when I had this enolate ion here, we're not going to protonate the O minus, right? We're going to protonate the alpha carbon. But what do I form after I do this right here? Like, what's the result of this mechanism that I just drew out in the laser?
Is that a carbo?
Carbonyl.
Oh no, I was something else.
Carbonyl. It's okay. It's okay. Carbonyl, which is what we had originally, right? And in most cases, we want to get to the carbonyl. But let's say this eno here is stabilized by conjugation, like there's a lot of double bonds right here, like that, then we don't want to get to the carbonyl, then we won't protonate the O-. It just depends on what you want to go into. If you want to go into the eno, then we want to protonate the O- instead this time to get to our eno, right? So it just depends on what your final product wants to be like, right? We want the eno if the eno can do a lot of resonance. If those double bonds were not there, like those were single bonds instead, then the carbonyl form would be major, like that. Okay. Any questions on this? Tautomerization mechanism in acidic conditions, basic conditions, eno to carbonyl, carbonyl to eno.
Is there a practice problem you could put up, maybe?
Yeah, I'm gonna put up a practice problem and then go over Aldol condensation after I go over some 118B stuff and maybe some 118A stuff. So I'm gonna give you guys, let's see here, how many do I want to give? Let's see. This. And I want you guys to practice the mechanism here, just for extra practice. Okay. Okay. Now the other one is going to be this right here. This is definitely important. Okay, try these two problems, but technically 4 if you split them into acidic basic conditions, right? 2 reactants here, but for each reactant, there's 2 conditions, acidic conditions and basic conditions. So try these 4, and I'll come back and check after. Okay, so for 118B, I saw your message, Sharon, if you're still here.
Yeah, I'm still here.
Okay. Let me answer this question. So we have this benzene with NO2, Cl reacting with these reagents, CH3, Cl, AlCl3. Okay, let's analyze this. We have a benzene with 2 substituents, a nitro group and a chloro group. And the reagents we have is Rx, a haloalkane, and a metal catalyst, AlX3. What reaction comes to mind when you see this starting material and this set of reagents here?
Would it be Friedel-Crafts?
Friedel-Crafts alkylation.
Yes.
Right. It's not acylation because there's no acyl group. There's no carbonyl there. So this is going to be Friedel-Crafts alkylation. And there is a common limitation for both Friedel-Crafts alkylation and Friedel-Crafts acylation. Crafts alkylation. Before I go over that though, let's analyze what these substituents are. Is this NO2 an EDG or EWG? Are you familiar with those terms, Sharon? EDG, EWG?
Yes. I
Yeah.
think NO2 would be a EWG.
EWG. And is that an activator or a deactivator towards the benzene ring?
A deactivator?
Yes, because it deactivates the ring, right? The ring here is our nucleophile in this mechanism. If we put an EWG there, we're stealing its electrons. We're withdrawing its electrons, making it a weaker nucleophile, deactivating the ring. So that's all we really need to know why this is going to be no reaction, because all Friedel-Crafts reactions, Friedel-Crafts alkylation and acylation, they do not work on deactivated rings. So that's the answer. This is no reaction because Friedel-Crafts reactions, both Friedel-Crafts reactions, alkylation and acylation, there's no reaction, does not work on deactivated rings. No reaction, right? This chloro group here is, okay, does that make sense, Sharon? Any questions on that before I move on to the chlorine and what's interesting about that?
Yeah, that makes sense. Thank you.
Yeah, of course. Now, I want to talk about this substituent here. Would you say that's an EDG or an EWG? And the strength of it, like, is it weak or strong?
I would say it's an EDG.
And why do you say that?
Because it's one of the exceptions because it's in halogen.
Yeah, so that's the thing that I wanted to get at. The halogen is the exception, right? Be wary of those halogens. This halogen here is going to be a weak EWG, electron withdrawing group. And the way that you could understand that is because halogens are the most electronegative elements we have in the periodic table, right? It's at the very right side of the periodic table, except the noble gases. But the noble gases are so stable, they're not going to be reactive. So next to that is the halogens, which are extremely electronegative. Because it has 7 valence electrons, it really wants to grab that 1 electron to be stable, to fulfill the octet rule. So because those halogens are very electronegative, they're going to withdraw electrons from the benzene ring very strongly, making it an EWG. But it's a weak EWG because it's not withdrawing groups by resonance. It's just withdrawing groups by induction, by electronegativity. And that's a weaker factor than resonance, right? Now, the exception here is that what is an EWG usually? An orthopara director or meta director?
Meta director?
Meta director, right. But in this case, the halogen, the exception, it's a EWG, but it's not a meta director. It's an orthopara director. The reason why is because when you do resonance here, there's going to be negative charges at the ortho and para positions relative to that EWG right there. When you draw out the whole resonance structures, you're going to see negative charges here, here, and here, directing the electrophile to the ortho and para positions. Now, let's say you have a benzene ring that just has the halogen, right? Since this is weakly deactivated, I've seen some professors have the Friedel-Crafts reaction still be able to happen, right? So I should say here, they do not work on strongly deactivated rings. Strongly deactivated rings, right? Because this halogen here is slightly deactivating the ring, but if that halogen was the only substituent there, Friedel-Crafts reactions can still happen because it's just a slight deactivator, a weak deactivator. This NO2 here, however, if I expand it out into its Lewis structure like this, where there's a negative charge on that oxygen and a positive charge on this nitrogen right here, it's actually going to withdraw electrons by resonance directly, right? It's going to like do all these arrows right here where we're going to have positive charges ortho and para to it, which is why the meta positions here are our best nucleophiles. Even though they're neutral, they're our best nucleophiles because they are better nucleophiles than positively charged, right? Positive charges are the worst nucleophiles. There's nothing there. Okay. Any questions on this, Sharon?
No, you covered it all. Thank you so much.
Yeah, of course. Okay. Any other 118B questions, topics you guys wanted to go over?
Can you over the Diels-Alder reactions? I was still a little confused on how you would, especially with the closed rings.
Yes, let's do the closed ring because there's a lot that goes into Diels-Alder. I don't know if you saw my previous YouTube videos, but like it required like multiple office hours to go over the Diels-Alder completely because there's a lot of things that goes to it. The regioselectivity, like the charges have to align, and then the stereoselectivity is like the endo rule, out group cis to EWG, in group trans to EWG, and then the dynaphile configuration as well, like trans and cis. Like, do those terms make sense, Sharon? Like those things I just said?
Yeah.
Okay, that's good. So let's go over a ring thing first, and I'm going to give it into a different configuration right here. So let's say we have this structure. I'm not going to say what it is yet. I want you to figure that out. Reacting with, let's say, this structure. Right here. And let's react this with heat. Okay. Now, 118B students, I want you guys to try this out, and I'll come back to you guys after I check the 8B students problem, and then I'll explain this as I check it. Okay. Have a screenshot of this, write it down, And I'll move on to 118A. Kelly, if you're still here, if you have any questions about it, like about your quiz today, your HNMR quiz, IR quiz, or whatever you want to go over today. Okay, moving on. Okay. So for 8B, have you guys predicted the products here?
I did.
Let me see.
Oh,
You
no.
can send it. It's okay. If you mess up, well, oh, it's okay, Madison. Let's see. Okay. So for the first one, we have this enol here, an alkene next to an alcohol, and we see that it could tautomerize into the carbonyl, right? But the carbonyl carbon is going to be that carbon there holding the alcohol. So we can have this carbonyl right here, where that pink carbon that I color coded is where the alcohol was at, right? And that's where the carbonyl is at now, and the double bond is no longer there. So based on what you drew as the reactant, that first product is correct, right?
I guess I just dropped the extra carbon.
Yeah, at the second conditions, basic conditions, it should be the exact same answer, right? Both acidic and basic conditions, if you tautomerize them, they should give you the exact same answer. What makes them different is the mechanism of how they got there, like that.
Question for the bottom, for the CH3, CH2OH, just ignore it.
CH3, CH2OH, this right here.
What's on the bottom of the reactants?
This one.
Yeah.
This one. Yes. That's a solvent. Just ignore it. But that
Okay.
will be used in the mechanism as a proton source to do things.
Okay.
So, yeah. Okay. Now for the next one right here, we see that this is the carbonyl form, but we see that its enol form is going to be more stable because these alkenes here can do resonance with each other, and it's aromatic. It's cyclic, it's planar, it's fully conjugated, and it has 4n+2 electrons, or an odd pair of electrons, making it aromatic and happy, right? So we want the enol form this time instead of the carbonyl form. Okay, so that's gonna be the answer for both acidic conditions and basic conditions. The mechanism I went over earlier, and that's a note card thing you guys can do, practice. Any questions on this before I move on? Wait, it's like if I highlight this pink carbon right there, that's this pink carbon right here. And Madison, I see you got the right answer for the second product, but you added this extra CH3, CH2 right there, which is now gonna be right there, right? Yeah, we're just gonna tautomerize, like if I outline this carbonyl right here, that's gonna be converted into this enol right here, alkene next to alcohol. CH3, CH2OH, just like these reagents here, just make that happen. But we're not gonna attach the CH3, CH2 onto the ring like that.
Okay, awesome. Thank you so much.
Yep. Does the CH3, CH2OH get used to remove the alkene? In this reaction here, down here, or in this reaction up here? The up one. So the CH3CH2OH is used to protonate the enolate ion that gets formed. So when this mechanism happens here, this CH3CH2OH job is to neutralize and protonate. Wait, actually, no. Let me draw out the mechanism here. See what's going on behind the scenes. Okay, so we have this enol, and we know that we want to convert this enol into the carbonyl in basic conditions, because we have this ethoxide and we have this ethanol here. So this ethoxide here is going to deprotonate this alcohol, give that oxygen a negative charge. Okay, now that's our enolate ion. We generated our enolate ion. Once we have this, we're not going to protonate the O- because that's going to go backwards to what we started with. We're going to protonate the alpha carbon here. Right, this is also an alpha carbon, but we can't protonate that. There's no double bond there. We protonate the alpha carbon that has the double bond right there. That's part of the enolate. Now, I know that my final product I want is going to be this carbonyl right here. So to do that, I'm going to reform the carbonyl, or form a carbonyl, carbon double bond oxygen like that. And I know that when I do that, this carbon here is now negatively charged in the resonance structure, which is going to get protonated by the ethanol. That's the job of the CH3CH2OH. Protonate the alpha carbon to give me this final answer right here. So if I highlight this hydrogen here of the ethanol in yellow, that's going to be this hydrogen right here in yellow. You do not have to draw that out in the mechanism or predicted product because it's a invisible hydrogen. So you don't have to draw that out, but to make it more clear on what this CH3CH2OH did in the mechanism, it protonated the alpha carbon to get to our final carbonyl answer in this mechanism. Yep. Okay. So let's go over Aldol condensation for 8B. This is going to be a sneak peek of what 118B is going to look like. But before that, as I say Kelly's message, when you draw out the elimination reactions for 118A, E1, E2, how do you know where the double bond goes if there's time later? Okay. So are you asking, because there's two types of elimination reactions, Kelly. There's E1 and E2. E2, let's do that first. The biggest thing to know where the double bond goes is the type of base you're using. There's a bulky base and there's a small base. These are strong bases, right? Small base. Do you remember the two bulky bases that you need to know? Well, you have Cagley, right? So I don't know if Cagley uses the same two bulky bases you need to know. But what bulky bases do you need to know for 118A for your class? Or does that term sound familiar? You might not hear bulky, you might hear hindered. Hindered base. Does these two sound familiar? Tert butoxide and LDA. Right, you might see tert butoxide in this form as well. And its solvent. And instead of K, you can see Na. I remember hearing hindered, but I don't remember what is considered hindered. I don't remember LDA. Okay, so if she didn't go over LDA, I wouldn't worry about that for her class, but for Helix class especially, and for Levin's class, you might want to know what LDA is for 118B and 118C. So terbutoxide here is bulky because this O- here is our base. If you look at the carbon holding the O- right there, there's 3 branches coming out of it. 1, 2, 3. Right, 3 substituents coming out of it. That's what makes it bulky, very hindered, very crowded. Right, so this is considered a hindered bulky base. Small bases are gonna be like OH minus, OCH3 minus, OCH2 CH3 minus, and even this is considered a small base. Right, because if you look at the first carbon attached to this O- here, this one carbon here has only one substituent, one branch coming out of it. Right, so that one branch is just gonna like stick itself outside of the reaction mechanism and not be crowded, right? But as long as you put one more substituent on that one carbon, that's gonna be considered bulky now. It's gonna be considered hindered now, right? So even this long thing right here, even though it looks bigger than this, it is bigger in terms of the length, right? But it's not considered bulky because at the reacting area, it's not as reactive, right? Because we're just worried about this area here. This area here. This area is way more bulky because that carbon has more substituents. Okay, so now let me give you simple halocane, and we're not going to worry about anti-periplanar transition state yet. We're just going to worry about regiochemistry on where things go. So if I give you a small base like ethoxide here and ethanol versus turbotoxide here in tert-butanol, do you know what makes an alkene more stable, Kelly? Like, what is that factor that makes alkenes more stable? Like, if I give you these alkenes right here, what would the order of stability go to? Like, what makes an alkene more stable? What factor? Right. If I gave you this list here, would stability increase from left to right, or would it increase from right to left? Okay. So the more substituted the alkene is, the more stable it's going to be. Left to right, yes. So it's going to increase like this. Stability is going to increase from left to right. Like that, right? But be careful here because she could change up some things in the question when she asks for energy. Energy is the reverse order. Right. So the highest energy is the least stable one. The lowest energy is the most stable one. And that's because of more substituents, more hyperconjugation. So in that case, this is going to be the substrate carbon, and these are the alpha carbons right here. I'm going to draw out alpha hydrogen A, alpha hydrogen B. Which alpha hydrogen do you think is going to lead to the more stable, more substituted alkene? A or B? Which one is going to lead us to the more stable, more substituted alkene here? B, right? Because B is more substituted. So a small base is small enough to reach that B, even though it's so crowded, right? That's the preferred hydrogen to make the more stable alkene. This small base is able to do that. So this small base here is going to grab that hydrogen B, make a double bond here between the substrate carbon, alpha carbon, and kick out the leaving group to give me this alkene right here that is tri-substituted, more substituted. Now, if I look at this butoxide right here, this butoxide also wants to grab that hydrogen B to also make the more stable double bond and kick out the leaving group, but it cannot do that, right? Because this is way too bulky, way too crowded. This is way too crowded, too much steric hindrance going on there. So that's not going to happen. What's going to happen is that this bulky hindered base is going to grab the most available hydrogen, the less crowded hydrogen, the least sterically hindered hydrogen, right? The less substituted hydrogen. Make a double bond right there, kick out the leaving group, and give me this mono substituted alkene right here. So there's going to be some specific names for this, and you might see this come up on the exam for Kaggle. I don't know how Kaggle exams are or quizzes are, but the more substituted alkene is going to be Zaitsev. The less substituted alkene is going to be Hoffman, right? So those are just names of what type of alkene we form. The more substituted, more stable alkene, Zaitsev. The less stable, less substituted alkene, Hoffman. You're going to come back to this at the very beginning of 118B when you learn about alkenes, right? Zaitsev versus Hoffman. Any questions on that, Kelly? Oh shoot, was I cutting off? Or did that make sense? Because okay. That's good. Now I'm gonna leave you off with this, and then I could check this in next week's office hours for you, or at the end. And this is gonna test about the anti-periplanar transition state. So I'm gonna give you two things here. Let's say I have this, and I have this, and I react it with two things here, NaOH and water, and CH3, CONA, CH3, 3, COH. That versus if I have this reacting with the same two sets of reagents here. Okay, so if we don't have time, I'll definitely go over this in next week's office hours, but try these for now, Kelly, and this will go over most of the things you need to know about anti-hyperplane transition state. I don't know if Kagli went over this, but just as a challenge problem, this is another one right here. Well, actually, I'll just give you two for challenge ones for E2. Okay. Yes. This. Okay. Yeah, try these 1, 2, 3, 4, 5, 6, 7, 8 problems here for E2 elimination reactions, and that would be good. Whoa, there's more things that goes to it, but I don't want to overwhelm you with the E2 stuff if Kagli didn't go over it. And this is more of a Liebens thing, because Liebens likes to go way more in depth with elimination for sure, with the rotation and everything. So I will just give you these for now. Okay, yes, I can go over part D from question 1 on practice midterm for 8B. And was the practice midterm quiz 4 or quiz 5 that you want us to go over? The one that Levin's posted. Quiz 4, okay, I can go over that. Okay, so before I go over that, let me go check 8B practice that I gave earlier. Here. What? Oh wait, yeah, I think we already went over that. Yeah, we went over this already.
I actually have a question about that.
Yeah,
So I was doing the mechanism for carbonyl to enol H2SO4.
This one?
Yeah. So after you protonate the oxygen, that's the first step, right? With the
Yes.
H2SO4. The next step is to take an alpha hydrogen, but the ring. Oh.
Do you see it now?
Yeah.
That's good. That's good.
Okay. There's only 2 double bonds on the ring.
Yes.
Oh. Okay.
So, like, when you get stuck, slow down, talk yourself through it, explain it like you're explaining it to someone, and you might see it. Like
Yeah.
Yeah.
I didn't realize until I actually said it out loud.
Yes, that's good. That's good. You're like, there's no alpha hydrogen here, but there's a sneaky one right here. Yeah. Yeah, that's the final mechanism.
Okay. Okay, that makes sense.
Yeah. Okay. Now let me check 1 and B practice here with the Diels-Alder, and then we'll do the practice that someone requested for quiz 4 for 8B. Okay. Okay. Can you send me what you have, Sharon? It's okay if it's wrong. We could avoid it for the midterm. Let's see this. 222. Okay. I see what you're trying to do. You're thinking of this as electrocyclic ring opening, ring closing, right? Which you drew these arrows here. Boom, boom, boom. But as a result of those arrows, we're gonna get this. Wait. You make that there, boom, 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 boom. this there. Yeah, we can't do that like based on those error. Wait. So you drew these arrows specifically. Let's say boom, boom, boom. That's double bond there. There's nothing there. That there, and there. Okay. So as a result of your arrows, this is what we should get right here. Right, which you did have with, let's say that's the methyl group right there, and this is the ester group right here, like this. Okay. So this is not going to be ring opening, ring closing. This is going to be a Diels-Alder reaction where this is sneaky here. The diene is in this orientation right here. The dienophile is in this orientation right here. So if I redraw this diene and rotate this molecule around like this, it might be easier to see what's going on. Like this. And the dienophile is right here. Does that make more sense, Sharon? Of what this reaction is going to be now?
Yeah, it does. Yeah.
Yep. Okay. Now, we have to make sure the charge is aligned before we move on. This is an EDG here, which when we donate electrons into it, there's going to be a negative charge at that part of the diene. This is an EWG here, so when we do resonance, there's going to be a positive charge on that part of the dienophile. So we got lucky here. We drew the diene and dienophile in the right orientation where the charges align, opposite charges attract, so we can proceed with the mechanism. If, however, they did not align, like let's say the positive charge here was down instead, or the negative charge was down instead, where they do not align, you gotta flip one of them upside down. And I like to flip the dienophile upside down because it's smaller and it's easier to flip and redraw, right? But in that case, we don't have to do that here. Now, once I have that, I then identify what's my out and in group. I'm gonna number this here like this: 1, 2, 3, 4, 5, 6. My out and in groups are only gonna be on carbons 1 and carbons 4. This group here going outside of the pocket, the green pocket, is an out group. This group going inside of the pocket is my in group right there. This right here is my EWG on the dienophile. Now, when I do the whole mechanism for Diels-Alder with heat, that's gonna give me this base product that's always gonna be there for Diels-Alder. That's always gonna be the product for Diels-Alder, where this is atom 1, 2, 3, 4, 5, 6. Now let's follow the endo rule here. We know that the out group has to be cis to the EWG. So let's make the out group a dash. That would make this aldehyde also a dash, because that follows the endo rule. The out group has to be cis, the same side as the EWG, dash and dash. Now the in group here, because it's fused in a ring like that, we're gonna make them trans to the EWG, which is trans like that, which is wedge like that, right? Like if I highlight this bridge here in purple, that's this bridge here in purple like that. Another way that you could visualize this is like this right here, right? Where this is 1, 2, 3, 4, 5, 6. At 4, we have this ester going down. And at 5, we have this aldehyde also going down like that, right? Where the yellow highlighted diene is this yellow highlighted diene right here. The blue highlighted dienophile is this blue highlighted dienophile. The purple highlighted bridge between 1 and 4 is this purple highlighted bridge between 1 and 4. The neo bond, the pocket that gets formed, is this neo bond right here in red, like that. So that's the mechanism and how we predict the product for Diels-Alder for its regiochemistry and stereochemistry, like where the groups are supposed to be at and how they are oriented, right? And don't forget the plus minus here, because everything could have been inverted. This could have been dashes, and these could have been wedges, and these could have been dashes right here, like that. Okay.
Well, I would be racemic if endo rule is always favored.
Yes. So it's gonna be racemic because endo rule is always gonna be favored. Because I could flip this into a wedge, making this also a wedge, and that still follows the endo rule. Because this out group here is still cis to the EWG, whereas the in group is trans to the EWG. So that still follows the endo rule.
Oh, okay. Got it.
Yeah. Nice.
Thank you so much.
Yes, of course. And I will have a worksheet ready for the midterm 3, not this week because I have midterm tomorrow. But after my midterm tomorrow, I will start working on that after my sessions.
Okay, sounds good. Good luck with your midterm.
Yeah, thank you. Okay. Now let's go over quiz 4. Wait, is she still there? Let's see. Are you still there? Christine? Yes, okay. Let's go over quiz 4. On question 1, part D. Quiz 4. Send a copy. Now, for the people who asked for Aldol condensation and Aldol dehydration, I went over that a lot of times on my previous office hours with the star and dot technique. So I recommend watching those videos on my YouTube for Aldol condensation and Aldol dehydration. Okay. Now let's do question 1, part D. Okay. I went over this as well. And one of my office hours. Jenna, Madison, you guys remember this problem?
Yes.
Can you describe to me the step-by-step mechanism on how we do this? Let's say I have this aldehyde, 2 equivalents of it. We have this strong base here, ethoxide. You could do the mechanism, or you could do the star dot technique. Which one do you guys want to do to predict the product? Since this is not mechanism, we could just predict the product right away. Right. But we know that before that though, we have 2 equivalent of aldehyde, strong base in its solvent and 0 degrees Celsius. What reaction do you guys think is going to happen here? What's the name of the reaction?
Aldol condensation.
Yes, Aldol condensation, right? Because what's the very first step here? What's this strong base ethoxide ion attracted to? What's it going to do? Is it going to attack the carbonyl carbon of the aldehyde and pop the bond onto the oxygen, or is it attracted to this alpha hydrogen right there?
Alpha hydrogen.
Yes, alpha hydrogen, right? Because if that alpha hydrogen was not there, it's going to attack that carbonyl carbon, but because it's there, it's going to attack that alpha hydrogen, generate the enolate ion, and that's my nucleophile. That's my first equivalent of aldehyde being used up right there. But sometimes she's not going to give 2 equivalent, and you have to assume it's an excess. So you might not even see 2 equivalent, but if you see nothing, assume this is an excess. I'm going to bring in the second equivalent of aldehyde right here, which is this. And now this is going to be my second molecule, where this carbonyl carbon is my electrophile. But what is my nucleophile in this molecule? Like, what atom is my nucleophile? Is it the O-? Is it this carbon, or is it this carbon?
The one on the far left.
The one on the far left, the alpha carbon. That's my nucleophile, which is why I'm going to star that. So when I proceed with the mechanism, I'm going to reform the carbon double bond oxygen, carbonyl, and have this starred carbon, alpha carbon, attack the electrophile, pop the double bond onto the oxygen, and give me this intermediate here. Now, this is the hardest part, in my opinion, for the mechanism. When you try to connect the 2 molecules together, the star and dot molecule, right? But what I recommend is draw out your starred molecule, copy paste like that. This is the star molecule right here. We have our double bond between carbon and oxygen back. We use this double bond right here to make a new bond between the star and dot carbon. This right here is a new bond between the star and dot carbon right there. Now, once we have that, we just copy and paste whatever is attached to this dot carbon. This dot carbon here is attached to this R group, which is CH2, CH2, and this alien looking arm. And it is no longer attached to a double bond oxygen, but it's attached to a single bond O- now, because we popped this double bond onto the oxygen in this mechanism. The hydrogen here of the dot carbon is still there, but I'm going to make that invisible. We don't have to draw that out like that. Any questions on how I got to this molecule here, where I connected the star and dot molecule together?
I have one question. I know we went over this before, but the on the far right, the O minus comes from. Oh, yes. Okay.
Yeah. The O minus comes from there because when we reform the carbonyl and have the star attack the dot, we pop this double bond onto the oxygen, which becomes the O minus. Like this highlighted oxygen here is this oxygen right here, right? Before it had 2 pairs of electrons, but now it has 3 pairs of electrons. It gained a 3rd pair of electrons. If I highlight that in red, let's say, that 3rd pair of electrons came from that bond right there, right? Which is why we don't see a double bond here anymore. We only see one bond because one of the bonds, 2 electrons, went onto this oxygen, giving it an extra pair of electrons and a negative charge. Like that. Okay. Now, the next step here is to neutralize this O minus with the proton source we have. And based on the reagents, our most acidic proton source is the alcohol. This O minus here is gonna grab the hydrogen, kick out the OR minus to give us our final answer for this Aldol condensation reaction with 0 degrees Celsius, which is gonna be this right here. Right, where we have an aldehyde and beta to the aldehyde, we have an alcohol. So alcohol next to aldehyde next to alcohol. This is an aldol, right? And we stop here. We stop here because we don't have heat. This is not heat, right? This is below room temp. Now, when we have heat, what is our product going to look like here? Like, let's just predict the product. Let's not do the mechanism because this is not a mechanism problem. How would we predict the product if we have heat and proceed with the Aldol reaction and do Aldol dehydration with heat this time?
The OH would turn into a double bond O.
This OH here becomes a double bond O like that? Or...
No, the double bond forms between alpha and beta.
Alpha, and the OH goes away.
Yeah.
Yes. Correct. So the OH goes away and we make a double bond between the alpha and beta carbon. No double bond O. Right. So that's gonna give us this final product right here. And what is the name of this product that we just formed? There's a name that you have to know about this product, and there's a specific set of reactions that you have to know for this type of molecule here.
Oh, dehydration.
Aldol dehydration is the reaction name that got to this product, but there's a specific name for this product.
Oh.
When you have a carbonyl and a double bond alpha and beta to it.
Alpha beta conjugated alpha beta unsaturated.
Yeah, alpha beta unsaturated carbonyl, and there's another name for this, which is also known as conjugated carbonyl. Right, so conjugated carbonyl is also known as alpha beta unsaturated carbonyl. And the types of reactions that you need to know for that is the 1,2 versus 1,4 addition with the irreversible versus reversible nucleophiles. Like that. Okay, because she can give another set of reagents here. Like let's say she puts this as the 3rd set of reagents. You are expected to know what this reaction does. When you have this, you might not even see it like this, but you might see the reactant starting as this alpha beta unsaturated carbonyl, and she gives you this Grignard reagent to react with. Right.
Which then that would be like a irreversible.
Yes. Irreversible because it's a Grignard reagent. That's one of the irreversible nucleophiles. And what would that do? Would it do a 1,2 addition or 1,4 addition? Would it attack the carbonyl carbon directly or the beta carbon?
Attacks the alpha carbon?
The
alpha carbonyl?
Carbonyl carbon, yes. The carbonyl carbon gets attacked by the irreversible nucleophiles. Right.
Okay.
Beta carbon gets attacked by the reversible nucleophiles. Yep. How do you determine the pKa for part 2A? Part 2A. So this pKa stuff right here, she went over it like a list of it in her lecture notes because I've seen her lecture notes. But that's one way you could do it. I don't like doing that way because like it's more pure memorization, which I don't like. I would understand what's going on behind the scenes instead. Conceptually here, low pKa means more acidic. More acidic means more stable conjugate base. More stable conjugate base means more resonance or more induction, right? So based on her list, around 3 to 5 is going to be the carboxylic acid hydrogen, G. Around 25 is going to be the alkyne, which is, where's the alkyne? Okay, 19 to 21 is the ketone, which is H. Around 11 is I. Around 25, now this is found on her lecture notes. 25, what is that? This is the alkyne one. This one I know for sure, but I can't find that here. Let's see, where is it? Is there something else? Carboxylic acid, ketone, that's taken right there. This is I. Aldehyde. It's not D. D is 50.
It says F on her thing.
F. Okay. It's F right here. Okay. That's good. Thank you. Okay, so that's why I recommend writing down what she put down on her notes, which is gonna be this right here on her note card. Where's the pKa stuff? Oh, right here. Yes. All this stuff right here. I copy these 2 pages. 2. Okay. Paste. Okay. So reference, alkane is 50, alcohol 16 to 18, oxonium ion -4 to -2, ammonium ion 9 to 11, amine 35 to 40, alkene 44, alkyne 25, carboxylic acid 3 to 5. Okay, so now this is where we see the 25, the other 25. So 25 here could be the alkyne right here, or this thing that she put on the quiz, the one next to the ester. But let's analyze why this is the case for the carbonyls. So if we deprotonate these hydrogens there and give a negative charge on these alpha carbons, let's determine the stability of these negative charges now. Let's look at the lowest one, which is this one right here. That it has the lowest pKa, meaning that this is the most stable negative charge, most stable carbonyl. And that's more stable because it could do the most amount of resonance. It could do resonance here and resonance there. No competition. Now let's look at the highest one, 25. This negative charge here can do resonance with the carbonyl here, but it's competing with the resonance with the thing on the opposite side, this OR minus here. This oxygen here has a pair of electrons that it could use to do resonance with the carbonyl, which is why, because there's competition, the pKa is higher, right? Now, if we look at this one here versus this one here, this negative charge has the same amount of resonance as this carbonyl on this side, right? So we can ignore that side right there. But this negative charge can also do resonance with the carbonyl on the left, making the pKa lower compared to this one. Now, if we look at the ketone and aldehyde and the negative charges at the alpha carbon, they do the same amount of resonance, right? But because the ketone has an R group, which is an electron donating group, EDG, that makes this less stable because negative charges repel each other. And because it's less stable, it's going to have a higher pKa value, less acidic, like that, okay? So that's how you could do that question for question 2A. Like understand the concept or write that stuff down that Liebens went over in lecture, right? But that's how you can also understand what's going on behind the scenes and why that's the case as well, right? Okay. So, yep, lower pKa, more stable conjugate base. Higher pKa, less stable conjugate base. That's the way that I would think about it. And the stability would be based on how much resonance it could do and how much induction it could do. Right, but know these values for sure. Write these values in your note card for sure. So I won't have time to go over like the different hemiacetal and acetal because I have another session coming up soon. But I probably went over that in my previous office hours, which you could watch on my YouTube. But yeah, good luck. Good luck. Tomorrow, guys. Good night, and you guys got this.
Thank you.
Of course. Good night, guys.
Thank you.
Oh yeah, Kelly. When do you have another quiz week 10? For 118A?
Yeah.
I see. That's gonna be about. Have you talked about organometallics reducing agents yet? Alcohols, ethers, those stuff yet, or not yet? What are you on right now? Like, what are you learning right now?
I don't remember.
You don't remember? Oh shoot! Yeah. Because like I know you have like stuff going outside. Like there's an incident, but
Yeah.
yeah. When was the last time? Like what was the last thing you remember though? What was the last thing you remember?
I'm looking. I sent you all the slides, by the way.
Oh, you sent me on the slides. Oh my gosh! Thank you.
I
Thank you
sent
for
it
that.
while you were talking. I just remembered.
Uh-huh.
But she didn't go over too much today because she gave us 45 minutes on her quiz.
Oh, that's good.
Yeah, last time she gave us 20 minutes.
Oh my god, that's more of a Levens thing. Like I think she was trying to like mimic Levens style because Levens also does quizzes every 2 weeks and it's also 20 minutes. And I also heard like Cagley also uses like Levens problem set questions as well, like the exact same identical ones. So I think Levens has been giving her like because she's a newer professor, Levens has been giving her material to use. But based on the feedback, like the 20 minutes was not enough time, huh?
No.
Yeah.
It definitely wasn't. Nobody,
Yeah.
like, barely anyone finished that.
Oh my god. What has been the averages been for Cagley's class?
The average, it's in the slides.
Oh my god, it's in the slides? Okay.
It's in the slides. Wait, hold on. Sorry, brain fart. What was I thinking? I forgot what I was thinking.
Oh, it's okay. Yeah, it's pretty late.
But today she went over started synthesis of alcohols.
Synthesis of alcohols. Okay. So that's when you start getting into alcohols. Like at this stage of 118A, this is when it starts to ramp up and start to get more hectic. More so be prepared for that. Yeah. But I will like help you through it when you show up to these office hours. Like just send me the lecture slides and I will look at it and then help you through it and organize it better.
It's a sad time.
Yes, it's a sad time right now. It's gonna be a very sad time.
No, it can't get sadder than this.
How many? Oh, wait, are you second or third year? Like right now?
Second.
Second year. I see. What other classes are you taking this quarter?
Biz 2C, ANS 108. And I have an internship.
Oh wow! Oh my gosh! From like, I see. And what's your major again? Sorry.
Animal science.
Animal science. Oh, are you trying to go to vet school? Are you pre-vet?
Yeah.
Okay.
Like everyone else.
Yeah. A lot of people I've tutored, like most of them are pre-vet. Like they want to get to vet school. Like all of them are pre-health actually, like pre-med, pre-vet, pre-dental, PA, like. But a lot of them I've seen are pre-vet, like with the horse. Like I didn't know you do Katya. Like you ride horses? Oh my gosh.
Yeah, that's how I got my concussion.
Oh, did you fall off your horse?
I did. I was bucked off.
Oh my god. Wait, was it a race? Like were you in a meet?
I'm not that kind of person because I'm not cool like that. But I'm like a beginner, so I was riding for fun. And then
so you didn't ride horses like all your life, like when you were a child?
Well, I wanted to, but my parents were like, we don't have money for that.
Oh my gosh. So like where are you from then? Like did you grow up with horses or
I I grew up in the Bay Area,
Oh, in the Bay Area. I see. That's interesting. Yeah. Dang.
and it's kind of expensive there.
Yes,
So,
yes, yes. I know, I know. I'm in there here right now. I'm in the Bay Area right now.
oh, and you have a
Yes.
midterm tomorrow?
Yes, I do. I have a midterm tomorrow. And I have a session coming up at 10:30 to 11:30 p.m. coming up in like 15 minutes too.
Oh, that's sad.
I know, I know. So after that, but I'm pretty prepared because I have like the resources sent to me. So I'm just gonna look at that. It's just a Quizlet, luckily. So
Mm.
if I look through that, I should be okay.
That's good.
Yeah. Oh my gosh.
Yeah, Katya's gonna meet tomorrow.
You and Katya's gonna meet tomorrow?
No, Katya's gonna meet tomorrow.
Oh
I'm
yeah.
gonna be chilling in my classes.
Yeah. I know. Katya told me that she canceled our session today because she has a meet tomorrow, and like one of her horses is gonna have a baby soon, like a baby horse.
Oh, Fluffy.
Yeah. Fluffy.
That's at the horse barn.
Oh my God. Wait, so did you just get into horses when you got into UC Davis, or were you into horses before UC Davis?
I did horses for a year in elementary school, and then I had to stop for financial reasons.
Oh.
But then I restarted back when I came to Davis.
In elementary school and in some middle school and high school, like you wanted to do it all the time, but you couldn't. But
I forgot about for middle and high school because everyone was like school.
Uh-huh. Oh yeah. I know. Dang. Oh my gosh. Do you know Briley, Jenna?
Yes, I
Oh,
do.
okay.
They were
Yeah.
my instructors.
Oh, they were? Oh my God.
They taught me for a quarter.
Oh my God. There's the horseback riding classes, right?
Yeah.
Oh my God. Well, I don't know. Let me actually move my laptop to show you. I don't know if you saw this yet, but let me just show you. Let me move this whiteboard out of the way. I don't know, it's not that clear. But that's Briley. That's
Oh,
Jenna. Oh no, that's Jenna. That's Briley. I mixed them up.
wow. How could you?
Oh my gosh, it's late. It's late in the night. Okay, Kelly. It's I don't know. It's so my brain is messed up right now. But let me show you.
Are
a
you
clearer
also
picture.
concussed?
Yeah. Yes. I cooked us after tonight's office hours. I need some recovery, but let me show you a clearer picture. I also went horseback riding with them too.
Oh, you
For
did?
one quarter, yeah.
Best computer ever. Yeah.
Yes. Okay,
This-
I'm not gonna mess up this time. This is Jenna. This
Uh-huh.
is Briley.
Oh, you got it
Yes,
now.
yes. Don't tell them I messed up.
I don't see them much anymore.
Oh.
They're not teaching.
Oh, they're not teaching anymore? Or
They're not teaching this year, I think.
I see. Yeah. This is the last year probably, huh?
I don't know.
I see. Interesting. Okay. Yeah, well, it was nice talking to you, Kelly. Hopefully I get to see you again next week in office hours. And it's gonna be more calm next week because like this week is crazy. Like a lot of people are showing up because they have quizzes and midterms coming up.
Mhm.
So after the midterms and quiz, like it's basically empty. Like no one shows up. I think
Oh,
people
okay.
just come up like right before the exams.
That sounds like it.
Yeah. Okay. Well, hope you feel better, Kelly, and good night.
Oh, thank you. Bye.
Bye.